Cerberus is just one piece of the puzzle, right? I would use an analogy of a rocket. Cerberus is the rocket engine, but you need more to build a rocket. Cassandra is building the rocket around Cerberus. Okay, we've got this great consensus mechanism for cross-shard communications, allows linear scalability. What else do you need, right? Cassandra now is at the stage where we're going to use it for a very public demonstration, the 1 million plus transactions per second. Right? And the interesting thing about this test is it's going to be dominated by community-powered hardware. It will have all the same kind of properties in the network topology as a mainnet. You'll have all the same latencies and packet drops and all those things that mainnets, and we'll be doing these throughput tests. So that then becomes a very strong kind of stick in the ground. Okay, we've done X number of TPS on these many validators across the globe. This is as close to a mainnet test of scalability as you're going to get without actually the network having any real value on it. And it should also put to bed a lot of the skepticism as well.
Today's Just the Metrics episode is all about linear scalability. But before going into this discussion, let me give you some context. So one of the outstanding ideas in the blockchain space that has got incredible market validation is the idea of an execution environment that allows full composability between all its applications. Ethereum pioneered such an execution environment, and it was a runaway success. The question was always how to scale such a system. With Ethereum following the layer 2 rollup scalability roadmap, that composability factor got destroyed. And the question is it possible to scale a distributed ledger supporting such an execution environment linearly? Meaning you add more resources to the system and the system will scale without breaking the composability factor. And that's exactly what we are going to discuss with Dan Hughes, the founder of Radix today. So without further ado, let's go into this conversation with Dan. Welcome to the conversation, Dan.
Thank you for having me.
Thank you for taking the time to be here. So this is one of the conversations I was waiting for so long to have, because Radix has a unique pitch when compared to other blockchains, like linear scalability through sharding without the need of something like a beacon chain, something like that. It is if you simplify the concept to the base level, if you add more resources, the network would scale to accommodate any need that could come eventually to the network. And at the core of that is the concept of Cerberus consensus protocol. But before we get into the nitty-gritty of Cerberus and the Cassandra test network that is going on right now, I think it's really important to know the background and the real motivation, like to understand where someone is coming from and to know your personal story.
Yeah. So over 10 years ago, in between things, I was in mobile wire working on both carrier integrations and systems and also on the device level as well, on the OS level. Before that, also working in NFC, like contactless payments and stuff. And a long time ago, I was a games developer, worked on some EA Sports games, Carmageddon 64, and a few other notable things. Fast forwarding to 2012, I exited previous company, was looking for something new, and stumbled upon Bitcoin. And my first interest was how has this Byzantine generals problem being solved in a permissionless way? So there's no permission validators or federation of validators. It's properly permissionless. You can join, you can leave, you can contribute. And that's been a long-standing computer science consensus problem. And people had attempted to solve it before, but hadn't quite got there. There's always an element of centralization or some centralized control. And so that was my initial interest. And then soon after that, we have to appreciate, the economic aspect of this is also extremely interesting in terms of the disruption, the opportunity, they're having a choice, they step outside of a traditional system and stuff. And having worked a little bit in the financial domain before with the contactless stuff, I've understood how the banking system works and how money is created, et cetera, and how it's all a bit of a scam. But to be blunt about it. And so I was very interested in Bitcoin and cryptocurrencies, and okay, let's dive into this. I mean, this is scratching two itches here. You got the computer science side of things, for all the gain theory stuff, the economic aspects, things, which are all very interesting. So I spent quite a bit of time just understanding Bitcoin at a very low level. How does the consensus work? How is double spend prevention working? How does proof of work glue all of this together? What are the economic properties of Bitcoin? Doing that task very focused and very thoroughly, and with a list of things that maybe go. So is this going to be able to scale? Because it's monolithic, and generally monolithic systems just don't scale, right? And is it going to centralize over time as you get concentrations of compute power for the proof of work and electricity consumption that's going to get high? How is the volatility of Bitcoin going to look over the macro term? And what impact would that have on small businesses and users? And one day it's up 10%, the next day it's down 20%. And that's not great for businesses like cash flow, right? Especially a small business, you need reliable cash flow and stuff. And so I thought, okay, let's see if there are any kind of solutions to some of these problems that I think might happen. And then spent some time in the Bitcoin code trying to figure out, are there any solutions for this? And I had some ideas, but they wouldn't fit into the Bitcoin code very well. I was trying to like get a square peg into a round hole. It just didn't want to fit, and came to the conclusion that Bitcoin is a great first step, but it's a first step, right? If these properties are required, the scale, the efficiency, the decentralization, then maybe take the fundamentals of Bitcoin from an ideology point of view, permissionless and self-sovereignty and all those things, but look at building a new protocol from scratch that can solve some of these problems. At the time, I didn't know if it was going to happen or if I was wrong. I didn't know if scalability would be an issue. I didn't know if centralization would be an issue. Obviously now fast forward over a decade and there are scalability issues and there are centralization issues and or potentially all the things that I thought might be a problem, that's be a bit of a problem. And so that's where my Radix journey started. And I was just at home in a home office, hacking away at things and ideas and trying out new things. And then small community grew around what I was trying to do, the ideas that I had, and what started as, okay, let's fix some of these problems or one of these problems and push out to the cryptocurrency, turned into, actually, let's do this properly and see if we can solve more than just one problem, see if we can solve the whole suite of things and develop a protocol that could potentially be extremely competitive for the top bot. And the rest is history, right? Fast forward a number of years, a number of iterations, research. It became a pure research project at that point for a number of years. Trying different things, throwing stuff away, starting again, lessons learned, and just build on those iterations until eventually you have a solution, ticks all the boxes that you need, and then that's when we start to build for them.
You have worked on this problem for so long, and I have read that you had a solution which was called Tempo, and you threw it all away and then started over again and ended up in Cerberus. Like, how was that process? Like, you worked creating a solution, completing it. When did you realize that, okay, this is not going to, and why did you actually throw it away?
Tempo was very close to the solution we were looking for. We achieved over 1 million transactions a second in a public test where we played the entire Bitcoin history onto Tempo. And I think it was something like 12 minutes or something. It was like 500 million transactions. But there are a couple of solvable issues around the consensus that I spent some time afterwards just investigating purely because I wanted to know, were they major issues or not? Did we just miss something? And they could have been solved. They weren't anything major, it turns out. The main thing that was missing was and not atomic composability, but atomic commit. That it was missing atomic commit. And without atomic commitment, you end up potentially with a lot of edge cases if things go wrong, and you need to have some mechanism to go and clean those edge cases up, or the developer of an application has to write code to go and clean those things up. Or in the worst case, the user has to clean them up by making another transaction. And so that was ultimately the nail in the coffin for Tempo. But again, with all of the iterations, every iteration since 2012, something has carried into the next iteration from the previous one, because it's not failing, it's learning, right? Some stuff didn't work, but some stuff was good. Okay, this piece is good, carry this to the next one, and then I can use this here, have some different ideas. And so there's a lot of the concepts within Tempo that are in Cerberus and Cassandra as well. Most of the sharding model is very close to Tempo's. A lot of the kind of philosophies and ideas around liveness and ordering make their way into Cassandra. There's quite a bit of Tempo in Cassandra, likely Xi'an too.
Great. The thing that makes Cerberus more complete than Tempo, as you said, is the atomic commitment part. Let's start from the basic. What is Cerberus consensus protocol? Could you describe it like in a high level view?
Yes, the Cerberus protocol, it's a cross-shard consensus protocol. So there's actually two pieces that you need. You need Cerberus that allows the shards to communicate, but you also need a local consensus within the shard as well, right? The validators within a particular shard need to be able to agree on what transactions that they want to process next, and what order they would like to process them in. And then once that's agreed, you can then have the Cerberus piece that communicates between shards so that you can exchange state and you can do the execution, you can produce the quorum certificates. And then the local consensus processes then again have their own consensus to agree, yes, the transaction is complete. Yes, this quorum certificate looks legitimate. Yes, we all agree that the transaction completed successfully and we will change the leg of state. So you have a local consensus process in each shard, and then you have these Cerberus consensus processes that sit above like a cross-shard consensus. So you kind of got intra-shard and inter-shard consensus processes for at the same time.
And the network is pre-sharded.
It's pre-sharded. One of the really early philosophies that I landed upon with sharding was you don't want a dynamic shard space, right, where your state lives, right? You want that to be static so that it's deterministic. So given any address, I always know which shard it's going to be in. And then with a very small amount of additional information about the network topology right now, I know which validators are responsible for that piece of state. And if you need to scale up in terms of throughput, it's much easier to move validators around and create additional validator groups than it is to say, okay, this big chunk of state data here, we need to split that down the middle, and you guys need to prune that, and you guys need to add to that. Right? It's much easier to move validators around than it is to move state around, right? Which is the approach that a lot of sharding mechanisms take is, okay, we're going to split the shard.
Yeah.
And then there's a load of data management that has to happen. Whereas if you pre-shard the state space, then you just manage and validate. If you say, okay, you're now moving over there, you're moving over there, and you're moving over there, great. Now we've got a new shard, which I call shard. So if you got a network where the throughput requirement is very low, let's say that your baseline throughput that a validator can handle, let's just say it's 100 TPS in the safe, right? So if currently your baseline throughput requirement is 50 and all the validators in the network can handle 100 happily, then you just have one validator group, and that validator group is responsible for all of the states, right? But then let's say that over time, the throughput demand goes up and it goes up to 120. And all the validators creaking under that load, we can't do this. So then there's a mechanism that is triggered that all the validators will agree, okay, we'll create two validator groups. One validator group will be responsible for one half of the state, and the other validator group will be responsible for the other half. And then they will come to an agreement on who is moving to where, who needs to keep some state here, who needs to sync some new state from somewhere else. You're not actually touching you're not manipulating the state address, right? The state stays in the same place, and it's just the validators that move around. Maybe they have to sync a little bit of state from here and drop a little bit of state from there, but it's just much easier to move. It's like the post line, right? If every couple of weeks your house moved, but your address stayed the same, it doesn't mean anything to it, right? Your house is in a different place, but the address that it has. Where's the house moved to now? the address says it's the same, but it's not here. Whereas, yeah, you can just get different postmen, have two postmen instead.
Oh yeah, the takeaway was that pre-sharded environment is much easier to manage than dynamic sharding, like moving around state.
Yeah, the important piece here is that given a wallet address and a small amount of metadata, you always know whom is responsible for it, even no matter what's going on in the network. If there's shuffling around, if there's lots of new validator sets being added, you always know who's responsible for it. Well, in many sharding models, you just given an address, you don't know where it is. You have to go and discover where that state is.
Okay.
You would ask some validators, hey, do you know where this is? And they'll go, oh, okay, that's some more. Where is this? Oh, I've got that. Whereas here, you just know who should have it.
In such a pre-sharded environment where you have two-step or two-layered consensus protocol like intra-shard and inter-shard, can we say that? In that environment, how would you make everything atomically composable? And could you then explain the difference in the idea of the concepts like atomic composability and atomic commitment? What is the difference, and how, first of all, how it makes atomically composable, and what is atomic commitment in that sense?
It's a little bit nuanced when you first think about it. So atomic composability and atomic commitment usually just get conflated together. So when someone's talking about atomic commitment, they'll say atomic composability. When someone's talking about atomic composability, they'll say atomic composability, right? But the difference is that atomic composability really refers to the execution, right? So given a set of instructions that I've composed together, I want those instructions to be atomic. And the strictest definition of atomic is either everything completes or nothing completes. So within atomic execution, all the steps of the execution that have been composed together, if there's an issue with any of them, all of the steps are cancelled, right? The execution cancels. Yeah. So that's atomic composability. Atomic commitment is you have an execution that is completed and that has been successful. And that might be an atomically composed execution. It might just be a simple transfer, whatever, right? And atomic commitment is different because that's saying that upon an execution being completed, all of the state changes should either be successful or none of the state changes should happen. So in the case of, let's take a swap as an example, right? So I want to swap from token A to token B to token C. So really I need two steps. So I'm going to compose two steps together. I'm going to say, okay, first I want to go from A to B because there's no A to C swap pool. Well, there is a swap pool from B to C. So I'll go from A to B in one step and then from B to C in another step. That's composed transaction, right? And the rule is that all of those two steps both have to complete, otherwise cancel the transaction, right? Let's say that A to B was okay, but B to C, something happened and the slippage wasn't what I expected. Between me composing the transaction and submitting it, something else happened. And so the slippage from B to C was too high. I didn't want it. That's okay. There's the execution of the set. And then nothing happens and I'm just still there all day. Yeah. Then the atomic commitment piece is, okay, A to B happened and B to C happened in the execution, and that was good. Now we're going to try and commit those state changes. Yeah. Now, if you don't have atomic commitment, what might happen in a sharded network is that the state changes that represent the swap from A to B might get committed on shard 1. For some reason, the state changes from B to C that need to live on shard 2, they fail, right? Whatever. Liveness issue, some validators go offline, communication issues, all the plethora of things could be wrong. It doesn't commit on shard 2, but it committed on shard 1. Now you've got a thought, right? Because now I'm left holding some token B that I don't want. So either the developer of that swap pool has got to then do another transaction to automatically clean it up for me, but then you've got to execute and commit another transaction, which also might fail. Or the user themselves has to then swap manually B back to A, and then pay fees, maybe some more slippage, and it's just a mess. So what the atomic commitment piece does is it says the execution was good, but it doesn't mean it's not home run yet. We've got to try and commit both state changes. And it's not possible to commit state changes on both shard 1 and shard 2. Both shard 1 and shard 2 should fail the transaction.
So atomic commitment part was the missing piece, as you said, in Tempo, and Cerberus fulfilled this atomic commitment part.
Yeah, because you could have atomic execution and atomic composability on Tempo, but there was no atomic commitment.
Okay.
Right? And in the strictest sense, atomic composability is dependent on atomic commitment, but atomic commitment isn't dependent on composability.
Yeah, because you can only do atomic commitment if everything is atomically composable.
Yeah.
But why is it so important? If I think about how Vitalik moved on with Ethereum and just went with the not so perfect solution, which is, and they knew it already, and they went with it, became overly successful, and then they were trying to change the system. You are taking an entirely different path. You are looking for that perfect solution. And in this particular feature, like atomic commitment, why is this particular feature so important? And why were you focusing on it?
Atomic commitment it's important in so many ways, right? So the most obvious one is the example that we've just been through. Right?
Yeah.
It reduces complexity. Even though so a complex piece in itself, but it reduces complexity on behalf of developers. It reduces complexity in terms of users. Developer and user experiences are much easier, much more streamlined if you have atomic commitment. Either it rings or it doesn't. That's it. Yeah, I'm going to worry about is it half committed or what have I got to do in these edge case stuff. It's important from that point of view, but it's also important from the point of view of your safety model as well, right? So atomic commitment, it's part of a bit of a duality role that it plays, or at least where it's important. So if you think about sharded network, your safety model is also important. You want to have deterministic safety in a sharded network. And where Ethereum struggled with their sharding proposals was they have probabilistic safety, right? And this is where a lot of networks have probabilistic safety, and then they have to have a load of like finality gadgets and all these other little things to get around the fact that their network is probabilistically safe rather than deterministically safe. And what causes the problem is, in our swap example, imagine that we've done a swap from A to B and B to C and everything went fine. But then if we have probabilistic safety models, then maybe there was an adversary in shard one that that's been secretly colluding and has created a stronger chain. And then after we've done our swap, they present that stronger chain to shard one. They're only in shard one because that's where they are, but they've created the stronger chain in shard one. And by the strongest chain rule, whether it's proof of work or proof of stake or whatever, the strongest chain rule, okay, this is the strongest chain. I'll bring that away, I'll go with this. Now we have a problem, right? Because in shard one, I've still got token A, but in shard two, I've got token C. I've essentially double spent, right? Because I've now got A and C from that original swap. And then how do we figure out which one is the right one? What happened over here? You did a swap. No, I didn't. There's no swap over here in shard one, and neither party can convince the other that they're correct. So you have a safety issue. But if you have deterministic safety, then one, you can prevent that. And two, you have atomic commitment, because if you're probabilistic, then your atomic commitment breaks, because even though it was atomically committed, something's been rolled back. So it wasn't atomic in the strictest sense, right? Because the integrity of that atomic commitment is now broken as well. So atomic commitment is really important. Again, it manifests itself in different ways, depending on the safety model, the liveness model, and all the manner of things. And this is why a lot of sharding models that were proposed for Ethereum and others they've been backed away from, because the fundamental properties of Ethereum just don't lend themselves to this atomic commitment that is so important, because the safety model is the wrong focus. Right? It's probabilistic rather than determined.
While looking at consensus protocols, it's like safety and liveness. There are models that focus on a deterministic safety and or like probability. Nakamoto family of consensus protocols, or BFT family of consensus protocol, they prioritize two different things. For Satoshi, it seems whatever happens in the network, miners can keep producing the blocks, and ultimately they would align on the longest chain, because that chain has the most amount of computational energy spent on. But when it comes to proof of stake, becomes a different kind of where is the most amount of stake is. And like coming to the liveness and safety, is Cerberus compromising on liveness when you focus too much on like deterministic safety and atomic commitment? Are you making compromise on the liveness side?
This is an interesting question, and it's a good question. Bitcoin prioritizes liveness over safety. Right? So it has a weak liveness guarantee. It's weak because something will always happen, but the interval between things happening is not guaranteed, right? Whereas with deterministic safety, and part of a consequence of the way that liveness manifests in Bitcoin is what gives rise to the probabilistic safety. So it's prioritizing liveness over safety. But with a deterministic safety model, you don't have any liveness guarantees under asynchrony. Yeah. But you have a strong safety guarantee. And now this is where I ended up in a quandary with Xi'an, Cerberus, etc. We need to have deterministic safety for the atomic frequency. That's a given. We need to have. But at the same time, if you think about, okay, let's fast forward the number of years, and let's say that there are 1 million transactions a second going over the network, always, and there are 100,000 validators, right? You know what happens if there's an issue? So, I don't know, 40% of the validators of the network are unavailable. Undersea cable gets caught, or a large portion of them are running on AWS cloud, which you shouldn't do, by the way. Decentralization, don't run your infrastructure on cloud. But people will because of cost, whatever, right? If there's no liveness guarantee, how do you get all those validators back? And what if they never come back? Right?
Yeah.
So then you've then got to orchestrate 60,000 validators somehow to agree to pack the node software because 40,000 have gone and they haven't come back. Who knows when they're going to come back and if they ever are, right? That's a huge logistical effort.
Yeah.
Orchestrating 60,000 validators across the globe in different time zones, and people who wouldn't have lives. Some might be on vacation, some are on a work trip, whatever. Yeah, you've got to try and orchestrate that as quickly as possible to get the network up and running. That's okay. Yeah, that's just not feasible at all. So we also need a liveness guarantee. Oh, great. So what we need is a novel hybrid consensus mechanism that Cerberus can sit on top of, but at the local instance, it needs to have both deterministic safety and a weak liveness guarantee. And that's been most of the Cassandra research is, how do you have that? How do you have deterministic safety also provide a weak liveness guarantee in the same way that Bitcoin does? So that over a period of time, your network will make some progress, and then it will eventually, it will slash those validators that are gone over time. Everybody can agree on that slashing, even if it's probabilistically safe for a period of time. And then eventually they get to a point where the validators that have left or exodus or stuck somewhere, and they will have been slashed to such a degree where the remaining validators constitute the majority of vote. But when the network is in a healthy state, you have this deterministic safety. When the network is in an unhealthy state, you have probabilistic safety and aliveness. That's been the bulk of my research with Cassandra.
So it is an ongoing process right now, the way I understand it. What is your learning trying to achieve the weak liveness guarantee and deterministic safety?
It's quite elegant. So I could, if we had another hour, I could explain to you fairly simply how you could take Bitcoin, you could modify some components of Bitcoin, and then Bitcoin would also have strong safety guarantee under synchrony and a weak liveness and probabilistic safety guarantee under async. And there's not a lot of steps to do it. Obviously, the time to figure out what those steps are, it's been a long time and lots of banging heads against the walls and things. But the solution to achieve a consensus mechanism that can give both, depending on the condition of the network, it's actually quite simple. And as always, the solutions to the hardest problems end up being simple and elegant.
Because you mentioned it, I have to ask it right now. Slashing, you have a bug in the software, and that resulted in this breaking the liveness of the system, and 40% of the validators go offline. Does slashing them is fair because those validators went offline not because of their own, like they are putting their own stake and participating in the network? It's why is slashing so important in that aspect?
Yeah, I use the term slashing because that would be familiar to
Oh, yeah. Okay. Yeah.
your listeners. What really happens in Cassandra is that those validators that aren't present, right, they don't get slashed, but the validators that remain, they accrue vote power, right? If all the validators are present, then for the proposals that get accepted, there's some incentive, some reward, right? Like an emission or whatever. And if your vote power is driven by state, and if your emissions to validators, your incentive to validators is an emission on an accepted proposal, then if a portion of the validators leave, then a portion of the validators stay, they'll be generating proposals between them. Every proposal will count towards their vote power. And eventually they will have accrued enough vote power or holistic safety mode that it dilutes away the vote power of the validators that are missing. So they don't actually get slashed, they get diluted away, right? If you do it for long enough, if those validators had 40% and then the 60% remaining, if you do it for long enough, then eventually the 60% will become 67% and you can have a fall.
Oh, yeah. Got it. Now I can comprehend that better, actually. Thank you. So in that sense, you are creating a network, even if you're like a linear scalable network should be able to accommodate like a lot of machines. And in that sense, Cerberus achieves this perfect, a very ideal or acceptable middle ground where you have like deterministic safety plus weak liveness. And so tell me more about the Cassandra network. Like what is Cassandra network? What is your end goal in that network? Like what is the purpose of Cassandra network and how this network leads to the Xi'an roadmap where the Babylon network would be able to scale linearly?
So Cerberus is just one piece of the puzzle, right? It's a very important piece, but there are other pieces to the puzzle as well, right? I would use an analogy of a rocket. Cerberus is a rocket engine, but you need more to build a rocket. Right? You need the body and the control surfaces and all that kind of stuff. Cassandra is building the rocket around Cerberus. Okay, we've got this great consensus mechanism for cross-shard communications that allows linear scalability. But what else do you need, right? For example, you could take Cerberus and you could put good old vanilla PBFT underneath for the local instances. Because Cerberus itself, it doesn't really care about liveness. It's ensuring safety across shards. That's where its focus is. So you could just put the permission PBFT underneath and you have a scalable permissioned implementation of Cerberus, right? Well, as we've just been discussing for the permissionless network, you also want some liveness guarantee, at least in certain circumstances. And so Cassandra part of our effort is, okay, we don't want PBFT, we don't want hot stuff because they don't give us any liveness guarantees. We need to develop a new local consensus method that does have those properties that complement Cerberus and what Cerberus is doing. And then by developing this prototype network with the new local consensus that gives us what we need plus Cerberus, okay, let's use this research network to look at other potential issues like authentication complexity when verifying signatures cross shards. How can you improve that? What's the minimum amount of data that you need to send from shard to shard in order to actually have a transaction execute correctly? How low can you push the bandwidth? How low can you push the CPU requirements? Because ultimately, we also want a good decentralization method too. We want all of the validators of the network to be commodity hardware. If the validator operators want to do that. Oh, I've got an old desktop machine from 2007. I'll just use that. I'll stick it in the corner and away it goes. Or low bandwidth internet connections. Like somebody the other day was participating in one of the Cassandra tests with a Starlink connection, doing just fine. Up to, I think they were final to about 7,500 transactions a second on the Starlink connection with an old laptop as well, like an i5 laptop from 2019. So that's all a good part of the research. How can you make this efficient? How can you reduce message complexity? How can you reduce the authentication complexity? What are the problems that we hadn't thought about yet? Bump into them. Okay, solve that. So when the team is building Xi'an, I've got a nice list of things. Okay, guys, you hit these problems. Here are some solutions for those problems. You might have to tweak them depending on how you're building it, but this is the broad solution to the problem. So it doesn't slow them down I can pack those bullets as I run ahead, so to speak. But also, aside from all the research enabling us to write papers on Cerberus and papers on new consensus mechanisms and figure out state model and how best to use aggregate signature schemes and all this kind of stuff, it also serves as a declaration that we know how to build Xi'an. Right? But here is a version of Xi'an, right? Production version is going to look different, but this is doing all the things network is going to do. It's doing a linear scale. It's got the liveness. It's got the safety. You can run smart contracts on it. Essentially, it is Xi'an. And then we could do these demonstrations and we could test things out and try new ideas with things and have some fun with it as well. Right. And so it serves multiple purposes. And at first I was a little bit, is this going to be worth the effort? It's been 10 times worth more than the effort. It's been invaluable to figure out big problems, little problems. They also give confidence to a lot of people as well that we actually can build this insane claim of a linear scalable network while still retaining decentralization as a fuse.
So what are the biggest challenges that you are experiencing right now going through the Cassandra network? What are the biggest problems that you're facing, or at least saying that, okay, this is like really hard problems to solve?
None, because they're all done.
Oh,
Cassandra now is at the stage where we're going to use it for a very public demonstration, the 1 million plus transactions per second. Right? And the interesting thing about this test is it's going to be dominated by community powered hardware. Right? So it's going to be Starlink connections. I'm sure somebody will throw a Raspberry Pi in there just to mess around with us. But then people will have powerful servers, fast internet connections, slow internet connections, all continents of the globe, doing all different things. Some of them will leave, some will rejoin. It will behave exactly like a mainnet. It will have all the same kind of properties in the network topology as a mainnet. You'll have all the same latencies and packet drops and all those things that mainnets suffer, right? And we'll be doing these throughput tests. So that then becomes a very strong kind of stick in the ground. Okay, we've done X number of TPS on these many validators across the globe. This is as close to a mainnet test of scalability as you're going to get without actually the network having any real value on it. And it should also put to bed a lot of the skepticism as well.
One of the main topics that comes into design choices for blockchains is like how decentralized is this system going to be? If you look at something like Sui, it's pretty much clear. The validator numbers will be some 100-ish. And if you look at what Ethereum, they really care about having thousands of validators. And from my personal experience, when I saw how a system goes from a federalized network state to a decentralized, was from me personally was Cardano. They had a incentivized testnet where 1,000 plus validators were participating. And then in the Shelley upgrade, it moved on to a decentralized block production with 1,000 plus validators. So it was an incentivized testnet. So going from a 100 validator state, which is right now the Babylon network, to something in Xi'an where you anticipate a network which could scale globally, that meant I anticipate like 1,000 of validator or 1,000 plus validators making a block. So how are you thinking about that transition? Because it's really go from it's relatively like a small validator set to a big one. How are you thinking about that?
Okay, so I think the first thing to bear in mind here is on the transition from Babylon to Xi'an, you don't actually need lots of sharding. You're not going to need 10 validator set all with 150, 200 validators in, right? Because Xi'an will come at the point when Babylon is at its throughput capacity, even with optimizations, and that would be great, right? You know, if we're churning hundreds of transactions per second through Babylon in the next, couple of years, that's amazing. But realistically, I don't think we're going to hit the Babylon throughput ceiling before Xi'an comes along. When the transition to Xi'an happens, Xi'an still only needs to be single group, right? Okay. Because in the testing that we're doing with Cassandra right now, the local consensus processes of Cassandra can handle a lot more throughput than Babylon. So we're seeing about 1,500 transactions per second per validator, whereas the upper limit in Babylon right now is around 100 at a put. So just on that transition from Babylon to unsharded Xi'an, you get potentially a tenfold increase in throughput, right? So those 100 validators come over to Xi'an, and they just essentially continue as normal. But the difference is in Xi'an, there won't be that hard limit. So more validators can be in the voting group. So you'll see the validator count start to grow 100, 300, 400, whatever. And then there'll come a point at some point in the future where the load in the network is too much. So you will then split those validators into two groups. Maybe you've got 250 in each group. And then more validators will join, and you get 300 in each group and 400 in each group. And then the load is up, so they flip to three groups and so on and so forth. And so it'll be a nice progression of decentralization. It won't be an overnight thing because it doesn't need to be.
Okay.
So it will, as strange as it sounds, as the network grows and more throughput is required, decentralization will increase.
So the demand should drive decentralization.
Demand should be part of.
Yeah.
Help to drive the decentralization. Yeah.
Okay. Now we can go to the questions from the community. And this is one question from Jackson. So are there any way to blacklist or whitelist particular shards getting involved in my dApps lifecycle so that I could prevent those shards whose availability guarantees I do not trust from getting involved in a critical step, or more generally, can we prevent important data from ending up in a faulty shard? What's the game plan for privatizing the leader schedule?
Okay, I'll answer the second one because that's easy. The Cassandra consensus protocol is leaderless. So much in the same way as Bitcoin operates, right? People are working to propose what's next, and then by some criteria, the strongest proposal for what comes next is the one that gets voted upon and selected. There is no leader in the sense of like you have with PBFT or hot stuff, right? It's manifested in the same way as it does in Bitcoin. It's random, it's non-pre-imageable, doesn't use proof of work, but you get the same properties from it. You could think of it, if you wanted to, without getting into the details, because we're getting through the time. If you had like a verifiable random number generator, you could use that to give you the same kind of properties that proof of work does. And you could use that random output that is secure and verified in order to select who the next leader would be based on the proposals that they generate. Right? It's not a leader protocol. It's leaderless. And then in terms of the shards, that's difficult to do here because I'm going to make an assumption about the way that they're thinking about sharding based on other sharding models. If I'm wrong, I apologize. Reach out to me on Twitter and we can have a bit more of a discussion about it if I'm incorrect. A lot of sharding models are very much application domain driven, right? Okay, this application lives in this shard, this application lives over here, this stuff lives over there. If that's the shard model, then of course it's very easy for you to say anything that comes from shard XYZ, you just reject it because that's an application that I don't trust, or the validators that run that shard I don't trust, etc. That's not how the shard model works here. Right? A piece of state where it lives in the shard space, and therefore which validators are responsible for it. When that piece of state is created, it's random, right? It could live anywhere. This is true state sharding. Whereas in the past, we've had transactional sharding, application sharding, all that kind of stuff. And I'm sure you've all heard about state sharding, and this is true state sharding in the strict sense as well. So you have no control where some state you create will live, because the way that the address of the state is generated is hash digest, which is obviously random and non-pre-imaging. Right? You can point to a piece of state and say, I don't want that piece of state to interact with my dApp. But there's no way for you to say, this particular group of validators that are currently serving this set of shards, I don't want to involve them, because you're potentially restricting users that you actually might want to enter that particular application, because the sharding model is an application-based or transactional-based or validator-based. It's pure state-based.
Okay.
The state is random when it's generated.
Now let's go to the second question, and this is about state bloat, because this is a big topic when it comes to the concept of inclusive accountability. Are there plans to combat state bloat? How will historical data be stored by nodes, data availability sampling? since the single shard group consensus mechanism is PBFT, they assume. What happens if one shard halts and the cross shard transaction needs to happen involving that shard?
Okay, state bloat. This comes up quite a lot, this question, in various guises. And I have different ways of answering it depending on the context of the question. And that question is quite broad. So I'll go with the broader answer that I usually give. State bloat historical state is only really useful if you want to audit everything, right? If you want to audit everything that's ever happened, then you're going to need all that historical state. Right? But from a pure consensus point of view, you don't need all of that historical state. All you need at any moment in time is confidence level that the state that you're using now has integrity, right? So maybe you keep a small window of state, the historical state, but all you actually really need is all of the current state. Yeah. Now, sure, in a sharded network, that might be a lot of state because, you've got all these different shards, you've got all these groups, you've got millions of transactions going around. But from a per validator point of view, the amount of current state they need to hold is quite small compared to all the static state. So from a pure consensus point of view, all you need is integrity of current state. Now, you have a number of options about the historical state. You could just prune it and forget about it forever because unless somebody needs to audit it, then there's not really a huge need for it. Even if you're a new validator that's joining, you don't actually need all of the historical state to be confident that the current integrity of state is good, right? Because you can do roll-up compressions, not zero knowledge ones, even more crude ones are fine. Every now and then, take a miracle hash snapshot, vote on that, etc. You could use ZK proofs or any other number of mechanisms so you can have a compact representation like a checksum, right? That kind of stuff. So even replaying, you don't need all the state. You just replay the portion and you're verifying the current state. There's a lot of options available for historic states, right? Some validators may choose, okay, I'll be an archive. I'll archive a lot of state, or that could be a service that's provided by somebody. Our plans on what that looks like for Xi'an, not really set in stone yet. There's a lot of options. We don't really need to think about it at this point. But the thing that we do think about is all that really matters for a network to operate is that the current state and maybe some historical has integrity.
Okay.
Push it off into IPFS or file it somewhere or have dedicated archive nodes or use roll-ups or some other compact representation.
So the next question is, why is the throughput of a single shard group in Cassandra test network far less than that of a high-performant unsharded L1 such as Solana, Aptos, or Phantom, for example?
Okay. That's because unsharded L1s are tuned and optimized to be fast on the sharded L1, whereas Cassie is developed to be cross-shard, linearly scalable, right? So there's a bunch of things that Cassandra has to do, whether it's sharded or not sharded, that affect the per shard performance. Certain primitives, certainly aggregation of signatures, the verification scheme, provisioning state inputs remotely, which is something that unsharded networks don't have to do because all the signaling is local. But with a sharded network, a state sharded network, I've got to go and fetch state from somewhere. I've got this piece of state, but I also need that piece, and that's over there. So I need to go and ask that for them, right? So you get some latency of IO, etc. So the per shard throughput is obviously going to be lower because it's doing things that have latencies, right? But I suppose that doesn't really matter because, let me think of an analogy here. Cassandra is geared towards linear scale, right? And those guys, Phantom or was it Aptos, which other ones were quoted, they're geared towards monolithic scale. Yeah. So they are like a very fast car, right? You can put some packages in that fast car and it can go very quickly to where it needs to go, right? I think Cassandra is like a truck with a builder on trailer. You put the same number of boxes on that trailer, well, the truck's slower, right? So it's going to take longer to get there. But when you have a lot of low scalability, yeah, you can only put 5 boxes in the car and it's going to go backwards and forwards, 1,000 times, right? You just pile one truck up with 1 million boxes and now the truck gets there quicker than the car. So the difference, right? It's meant to be fast, but there is a strict upper limit of how fast they can go. And that strict upper limit will at best fall in Moore's law, right? Whereas linear scalability in terms of you throw in more compute, that's like the big truck. You just keep piling more and more trailers on the back of the truck, and it just takes more and more along with it. It's not really an apple to apples comparison because we could just add more trucks.
Oh, yes.
Validate, keep adding trucks. Yeah, the trucks are a bit slower than the car, but they can carry more.
Okay. The next question is, could privacy tech like CK tech could be incorporated at the consensus or execution levels of Radix? Could this improve systems efficiency?
Yeah, I mean, I still think about privacy quite a lot. Privacy is one of those things that is important to me and Radix too. But I think privacy it can wait a while. It's not something that's as urgent as like development experience or user experience or even scalability. But I think privacy will start to play an ever increasing need, I think, over the longer term in these kind of technologies, crypto, Web3, etc. Yeah, like the pays or some of the solution to that, I think, depending on the application, what it is you're trying to do. Protocol level privacy, also obviously an option, which you could use some ZK tech for as well, and some softer ways of doing it that aren't quite as intensive. It's a sliding scale of cost versus reward in terms of effort. And then you have other uses for L2s as well, such as application specific uses. That's really where I think L2s have utility. L2s shouldn't be scaling solutions because they just, you see it surely all the time, right? There's 20 different L2 flavors on Ethereum, and now people are talking about L3s and L4s. It's in before L100. There you go. I win. Yeah, they shouldn't be a general scaling solution. There could be a scaling solution for application, right? Like if you want a high frequency trading depth, L2 is perfect for that, right? And for some privacy stuff too, L2 is perfect. But again, it's application domain, right? Not protocol domain scalability and that kind of stuff. L2 should be a general scalability solution, and they are not the solution to all problems people either. Stop. What's the saying? To a shiny new hammer, everything is a nail.
Next question is intra-validator and inter-validator sharding. What do these terms mean, and which one will Radix use, and what are the different pros and cons of both?
So Radix is using inter, and inter is where you have some validators in one shard, some validators in another, and they're talking to each other, right? And intra-validator sharding is where you have a validator, a primary validator that is network facing, and there's maybe 100 other primaries, right? Behind each primary, there are a number of secondary validators. The primary talk to the secondaries talk to the primary, they share workload behind the scenes, and then when the workload is finished, they give it to the primary, sends it to all the other primaries in the network. Those other primaries in the network then give it to their secondaries who do validation or voting or whatever they do. And that's your intra-validator shard. One is behind the scene, and the other one is network based. The benefits are obviously I'm biased. I think one of the benefits of inter-validation sharding is you can see who's in the network, right? You can see all the validators, you can see all of the compute. It's very easy to look at the network and calculate a decentralization metric. Now, you might have some operators or validators that have secondaries in their own kind of infrastructure. That happens too. But if the majority of your network is inter-validator sharding, then that's one of the benefits. And you also potentially have a higher security metric as well, because the vote power is distributed more. Okay. So let's say, for example, we have 1,000 validators in the inter-sharding network, and then we have 1,000 validators in the other, but there are 100 primaries and 900 secondary validators, right? Which means the distribution of vote power is what's more concentrated over here, right? Because the primaries are the ones that have the vote power, and the owners of the primaries are the ones that also own the secondaries. Yeah, so you've got a lot of compute, but the state is concentrated around those 100 actors, whereas in the inter-validator, where all the validators are network facing, the state is distributed amongst those thousands. So you get a better security metric because it's harder for somebody to come along and collude with 1,000 than it is with a 1. So one area where trap of validator scaling is useful is a very high load network. So like an unsharded network, right? You can load balance heavy IO, read and writes to persistent storage behind the scenes. You can do very parallel execution of transactions, which is something that is doing.
Yeah. Pilot fish, I guess.
Yeah. So there are some benefits, but I don't think that they outweigh the Radix inter-validator approach, because given those same pairs of validators, you're getting natural load balancing anyway, right? Because you can put those 100 are in one shard with all the 900 secondaries. These 1,000 over here are in 3 shards. You already load balance at 3x, right? Because you're sharing the IO, because the data is split into 3 partitions, essentially. You have parallel execution because some transactions will be happening and being verified in shard 3 that don't even touch shard 1, so they didn't even care about them. They're processing different transactions, so you get some parallelization anyway. And you can still do execution parallelization with the validator itself, the cores doing execution, right? I don't really think there's a huge amount of benefit. The only benefit, I think, where it counts is if your stack is monolithic and you're stuck with a monolith. That's where the benefit is. If you make some gains in terms of IO latency and execution.
And going back to your opinion on L2s, should these are specialized use cases. If you look at Solana, they are focusing very much on latency. Anatoly's vision is to bring NASDAQ on blockchain. Yeah.
No.
Go. Why it won't work, actually?
Okay. He's obviously talking like NASDAQ high frequency trading, right? I'm assuming his vision for that is that lives on the Solana main chain and not in an L2 somewhere, right?
Solana mainnet, yes. Yeah.
The latency is just too high. No senior trader is going to use it. Those guys are used to having fiber cables, dedicated fiber cables, close to the NASDAQ exchange in the next building, so that their latency on the order book is 3 million of a microsecond. And then Anatoly is going to achieve that similar latency on Solana with its 2,000 validators. It's just, it's like, unless all those validators are in the same room, then it's going to be, even if they're in the same country, he's looking at 2 nanoseconds. And these guys that do these higher frequency trading are used to microseconds because, like I say, they've got a dedicated connection to the exchange and the exchange is next door. No, it can't be done.
So, what if it's not like high frequency trading, but it was more talking about some news event like happening, and when it causes some price movement. So there is no inequality in information dissemination in the sense that, okay, something happens somewhere in the world, and that
all the traders next door to the NASDAQ have already seen that news and put trades in on it before all of the Solana validators have even agreed it's news. Can you send me like a reference to this? Because maybe I'm making assumptions that I shouldn't.
Oh yeah.
Maybe I'm talking out of order about what he's saying and what.
I can send you some links that, and then we can see if we should.
He's a smart guy. I find it strange he will be making those kind of claims. Maybe I'm jumping to assumptions when I shouldn't be. You could send me whatever it is you see.
Yeah.
I'll get back to you with my thoughts on.
And the second last question is, what does braided shards actually mean?
Now we're getting into it. Okay. They usually, consensus mechanisms tend to work in like a single 30 block step. Let's think we're like that. Somebody, whether it's a leader or in a leader list, whatever, it doesn't really matter. Somebody proposes something should happen next, right? And then that proposal gets broadcast to all of the validators of the network. And those are the validators of the network. Look at the proposal or proposals, depending on what's happening, but we'll just keep it simple. Look at that proposal. And if they agree on the proposal, the order transactions, whatever these transactions are in there, they will then vote back to the leader. So let's keep it simple. Leader proposes, everybody looks at it. Yeah, this is good. They send a vote back to the leader, right? If the leader receives a majority, supermajority of votes saying, yeah, this is good, then the leader signal to everybody, yeah, here is a certificate that says, that proves that a supermajority of all of you got back to me and said, we like that. So here's the proof that you need to be sure that we can execute it. So please go ahead and execute. So that's phase one, propose. Phase two is now go ahead and commit. So like a pre-commit, right? Then all the validators receive the certificate. Okay, leader says this, check the signatures, everything. Yeah, that's cool. We will do the commit. So they do the commit, and then they send back a signal to the validator, to the leader to say, commit was successful, commit or commit was bad. So then the leader collects these responses, and depending on the outcome, it puts together another certificate, says commit was good or commit was bad, and here's the proof of what the supermajority, either supermajority said it was good or supermajority said it was bad. Since that, there's a kind of final cleanup, a final phase on the commit where all of the validators then receive the certificate from the leader. All good. Okay, cool. Round is finished. Everything is committed, and then they confirm the commit back to the leader. I did that. I did the commit. Leader then creates another certificate, depending on if it's a 2-phase or a 3-phase mechanism, which we won't get into. But sometimes there's 2 phases, which is that is a proposal, commit. Then sometimes there's a third one as well, depending on your consensus mechanism. So what braiding does is it interleaves those phases together. Because if you have a leader that has proposed something while you're doing the verification and the voting and the commitment to that proposal, no one else is proposing anything. No one else is, because it's single thread. Yeah. Okay. Proposal, we'll work on this. Okay, finish that one. Next proposal, let's make that, send it out. Very lockstep, very, very organized, right? But you can break them because if you know who the next leader is going to be, yeah, you can say, okay, this leader here proposes, and then when this proposal goes into the commit or pre-commit stage, depending on how many phases there are, we know who the next leader is going to be based on this proposal. So they could actually start a proposal and they could send that to the network because the network knows who the next leader is for the next round. So they could then do a proposal. So they do a proposal. This goes into commit. This goes into pre-commit. And then because this is in the pre-commit stage, if that does get accepted, everybody knows who the next leader is. So they could also now propose something. So you've got this one's in the commit, this one's now in the pre-commit, and this one's in the propose, right? It's for, instead of previous where you would have only one proposal being committed for every 2 or 3 phases, depending on your consensus mechanism, now you're getting a proposal being committed on every phase. So you get a throughput.
And now the question is about the like finality and latency of the Xi'an network. What do you anticipate?
Yeah, I can actually give you honest because we've been testing this just this week for simple transactions. And I want to make this important clarification as well. So in Babylon, in Cassandra, and in Xi'an, even a simple token transfer from me to you is very smart contract. It still does a lot of the same stuff that a smart contract call would do, right? So the cost is about the same. Yeah. The kind of testing that we've been doing, everything in Cassandra, by the way, is a smart contract. There's no like cheap transfers that we can claim boost our TPS like a lot of projects do. We are seeing finality of 3.5 to 4 seconds. And there is room for improvement there as well, because the Cassandra code base is very unoptimized. It's raw, right? Because it's research. It's not about pure performance. Even though it's about linear scale, it's not about pure per validator performance. Yeah. Optimize later. Let's get the theory right first. So there is room for improvement there. So we're seeing 3 seconds, 3 to 4 seconds on a simple transfer. And this is the global validators and different continents, Starlink and all that stuff. If you go to slightly more complex transactions where maybe it's touching 4 or 5 pieces of state, so it's having to touch 3 or 4 validator groups, then you're looking at about 6 seconds. If you go more complex than that, say you're touching 10 groups, you're looking at around 7.5, 8 seconds, because it's logarithmic in Finality, right? The more groups you touch, the less of an impact it has in that Finality metric because it's logarithmic in terms of its increase. So your biggest step up in Finality is going from 2 groups to 3, right? And then from 3 to 4, it's less, and then 4 to 5 and so on. And eventually, you're at like 100 groups, and it's 12 seconds almost. That'd be a really complex transaction as well. That would be like the mother of atomically composed transaction. So Finality is pretty good already, and it's not even optimized yet. There's at least a good 30% still in there. And then in terms of throughput, at the moment, each validator group can do about 1,500. But again, and I've already profiled this as well with some tooling. There is at least 50% more there if I wanted to spend the time to optimize it. So you're looking at maybe 3,000 to 4,000 transactions per second per group with those optimizations. And this is on hardware, which is 4-core, 8 gig SSD, low level hardware, low spec hardware as well.
And finally, when Xi'an?
I ain't giving no dates on Xi'an. There's still a lot of work to do. And right now, people focus a lot on Xi'an all the time. And I understand why that is. And obviously, I focus a lot on Xi'an because I do the Cassandra stuff, right? So I'm myself focused on Xi'an quite a lot. But really, Babylon is the more important of the two, because Babylon is what will grow the ecosystem so that Xi'an is needed. If Babylon isn't successful, Xi'an isn't needed. So Babylon is the most important of all the network releases. Xi'an complements Babylon because Babylon, if it does what it needs to do, Babylon will bring us millions of users and, dApps and infrastructure, and the ecosystem will flourish. And then it will get to a point where Xi'an is needed because it's so thriving. We need to scale it. And so people should focus some attention on Babylon as well, because Babylon is the most important of all of the 3 releases. Olympia was obviously important because it was the start. But Babylon is what takes us to the top of the charts.
Fantastic. That is the right place to conclude this conversation with Dan. I learned a ton from this conversation, and thank you so much for taking the time, and enjoy your beer. And
it's probably warm now.
Yeah, most probably. Grab a new one and enjoy your evening. I wish you a fantastic weekend, and hopefully we will catch up soon again.
Let's do another one sometime. Yeah, cool.
Yeah. Thanks for tuning in. If you are keen on getting deeper insights about Web3 tech, our newsletter, Just the Metrics, is just what you need. It's packed with valuable information, and it's completely free. You can subscribe by clicking the link in the video description. It's a great way to keep up with the latest in the Web3 space straight to your inbox. And before you go, please hit that like button and don't forget to subscribe to our channel for more updates and insights. Your support is what keeps these videos coming. So see you in the next video.